So I think that's all continents, right?
Yeah, I think so. Pretty much.
All right, so we will start our session. Again, welcome everyone to the third live session of Learning Geology, Geology of Volcanoes. Learning Geology is a community organization that aims to promote geoscience literacy worldwide. We have a great team of editors who help us create a variety of content to promote geoscience literacy and provide geoscience education. Today's live session is one of the 7 geoscience outreach sessions by Learning Geology. We have experts from different fields, and these are free live sessions. Please join us in the upcoming days for these live sessions. These are again free, and they are open to everyone for all ages, for all backgrounds, and you can register using the link shown on the screen. So our today's speaker is Denali. Denali is a volcanology and geochemistry PhD student. Denali has been working with Alaska Volcano Observatory. Denali is also doing amazing geoscience outreach work on TikTok with more than 250,000 followers. So that's a huge amount of outreach work Denali has been doing. Myself, I'm Mohammed Qasim, and I'm a co-founder at Learning Geology, and I'm also a PhD student at the University of Prince Edward Island in Atlantic Canada. Today's session is about geology of volcanoes. You will learn how volcanoes form, why some of them explode, why some don't, and how you can prepare for eruptions, and how to spot misinformation on social media, like about the Yellowstone volcano. I'll hand over now to Denali.
Yeah, perfect. Okay, give me just a minute to share my screen. And I will get my little laser pointer set up. Okay, so we can go ahead and get started. I'm going to be talking about the geology of volcanoes. And my name is Denali. I'm a volcanology and geochemistry PhD student, or at least I will be starting this fall. Until then, I actually work at as a laboratory technician at a volcano observatory, like he said, and I also work as a marine geologic contractor. My undergraduate thesis was on underwater volcanoes, so I get to do a little bit of both of those fields, which is very, very cool. I'm here to teach you about volcanoes, both the basics of how they work and also some of the more practical stuff, like what you should do if you live in a volcanic area, what you should do during an eruption, and as you said, how to spot misinformation on volcanic systems, because there's a lot of it out there. I'm looking at you, Yellowstone Volcano. And so what is a volcano? A volcano is a vent or opening in the Earth's crust where volcanic products like lava, ash, pyroclastic flow, and other fragments can be ejected. And we're going to go over those different hazards as well as a few others in a little bit. But first, I really wanted to go over how they form. A lot of people tend to think that volcanoes just kind of exist and eruptions happen only at places with like a pre-existing cone, like is shown in this photo. But something had to create that volcanic cone, right? There had to be a first eruption at that location. And one of the areas where volcanism can occur is called a subduction zone. Earth's crust is made up of different tectonic plates. And when one of those plates is subducting underneath another one of those tectonic plates, this is something that's usually determined by weight or density. So whichever tectonic plate is denser, heavier, is going to be subducting underneath the lighter plate. And as the plate subducts, it goes deeper and deeper into our mantle, which is very, very hot. So it starts to melt. And this melt of magma rises to the surface and forms volcanism. Lots of volcanic areas around the world are the result of subduction zone volcanism, including the Western United States, Japan, New Zealand, and a lot of South American volcanoes are all related to subduction zone volcanism. This volcano is a volcano called Volcan Fuego that I was at earlier this year, and it's the result of the Cocos tectonic plate subducting beneath the Caribbean plate. And this produces the entire Central American volcanic arc. So there are a lot of volcanoes in that region, and they're all formed by subduction zone volcanism. Hotspot volcanism. Hotspot is another area that is very likely to experience volcanism, and a hotspot is essentially a plume originating deep within the earth that is superheated compared to the rest of the mantle, at least. And so when it makes contact with our crust, it causes melting. And a lot of very famous volcanoes are hotspot volcanoes, including Yellowstone, the Hawaiian volcanoes, Icelandic volcanoes, the Galapagos are all created by hotspots. And you may have noticed a lot of those things I listed are islands, and that's because hotspots can happen beneath a landmass, an existing landmass, but like in the case of Yellowstone, but a lot of hotspots are located beneath oceanic crust. And what happens in this case is that the plume stays stationary and our crust moves over it. And as the tectonic plate moves over it, that plume creates a series of volcanic islands. Using the Hawaiian volcanoes as an example, you can see that as the plate has moved over the plume, it's created the Hawaiian Islands, and the newest island, which is has already been named but is still pretty much underwater, is forming. And I should mention that newest in this scenario still means it's already been forming for hundreds of thousands of years. So keep that in mind when I say new, we're talking about geologic time, not necessarily human time. Hotspot volcanism and what causes it is actually one of the big mysteries in geology. We know a lot about them because we know that they exist because we see the result of them, which is all these volcanoes. But what actually causes them to occur is a point of pretty big controversy among a lot of geoscientists. And that's one of the reasons why hotspots are by far one of my favorite volcanoes. I was lucky enough to do some field work at the Fogoradas Fall eruption in 2021, which is where a lot of my favorite fieldwork photos are. It was definitely a life-changing experience and why I'm doing my PhD on Icelandic volcanism. A divergent boundary is another area where you get a lot of volcanism, and that's an area of the Earth's crust where the two tectonic plates are diverging apart as opposed to coming together like they would at a subduction zone. So those two tectonic plates are moving apart, and the lava directly from the mantle comes up between the diverging plates. Eruptions at mid-ocean ridges are the most, you could say, I guess, pure representation of the mantle, as close as we're going to get, because it's coming directly from the mantle to the surface without having to go through a lot of material in Earth's crust. If you look at either subduction zones or hotspots, you can see a majority of the time this this magma has to go through a lot of crustal material before it can reach the surface, and that's going to change the composition and some features of the lava. At mid-ocean ridge volcanoes, you don't have that kind of interference with the composition as it comes out of the mantle. And divergent boundaries are actually what forms our ocean floor. So these are called mid-ocean ridges. That's where new ocean floor is forming as the plates pull apart. This ridge right here is one of the most well-known ridges. It's called the Mid-Atlantic Ridge, and that's the ridge that Iceland is located on. So Iceland is a very unique region of volcanism because it's located on both a hotspot and a divergent boundary, which is why we have so many eruptions. The entirety of Iceland, for the most part, is volcanic rock and formed from volcanic eruptions. The discovery of the Mid-Atlantic Ridge by a woman named Marie Tharp is actually what proved the theory of plate tectonics. So this idea that the Earth is made of tectonic plates that are moving was originally very, very controversial. But when the Mid-Atlantic Ridge was discovered, it proved that theory. And this is because as the plate diverges apart, and the area in the center is filled with lava and solidifies, like we said before. But when it happens over and over and over again, where it keeps opening and filling and opening and filling, these areas get pushed outward, like the arrows show. And as these regions get pushed outward away from the primary axis of the ridge, that is one of the things that causes our continents to move apart. We used to be part of one large landmass called Pangaea, and now we have multiple continents. And one of the drivers of that is these processes at mid-ocean ridge and the volcanism at mid-ocean ridges. I think mid-ocean ridges are one of the most fascinating things on the planet. They're 100% the reason why I got into geology in the first place. I read about them in an oceanography class before I even became a geology student, and I didn't never really think much about underwater volcanoes, and I heard about them and I went, oh my gosh, that's what I want to study for the rest of my life right there, which is why I did my undergraduate thesis on submarine volcanism at a mid-ocean ridge called the East Pacific Rise, under the supervision of some really incredible scientists from University of Florida and Woodsville Oceanographic Institution. But what's really amazing is that not only do submarine volcanoes exist, but they account for above 60% of volcanism on Earth. So actually a majority of volcanism on Earth is from underwater volcanoes, which I think is very, very cool. All these red lines on here are mid-ocean ridges. So it's the largest volcanic system on the planet, and yet there's still so much to learn about it, and a lot of people don't actually know about it, which I think is really neat. In order to collect samples and research these kinds of volcanoes, they do have to be collected from the bottom of the ocean, which can be done several ways. They can be collected by robots. So this is an ROV, or a remotely operated vehicle. This one is named Jason, and this is what collected the sample to the right, which is one of the ones that I used for my undergraduate thesis. And this is what that collection process might look like at the bottom of the ocean. So these are called pillow lavas. And here are some hydrothermal vents or black smokers. And then this is the robot arm collecting one of the samples. And this is a very cute little deep sea crab right there. And samples can also be collected using an HOV, which is a human-operated vehicle. This is the submersible Alvin on the right. I have not yet been in an Alvin, but this is my undergrad advisor, Mike Perfit, in one. And he actually talks about his experience as an aquanaut who explores the ocean floor in this article here, if anyone is interested. Reading that article is another thing that really sold me on becoming a geologist before I was even his student, because he talks about how everyone in the Alvin has an Alvin snack and that they eat when they're down there at the bottom of the ocean, and how his is a PBJ. And I just thought, you've got to be kidding me. You can get paid to eat a peanut butter and jelly sandwich at the bottom of the ocean. I've obviously found my dream career. But one of the most important things that he taught me is to be passionate about sharing my love of geology, which is a big reason why I do a lot of the outreach that I do. So feel free to check out that article if you'd like to learn more about that area of volcanic research, since we don't have time to really go into that in detail here today, and I could fill an entire session just on submarine volcanism. We're going to get back to the other kinds of volcanoes. If you've ever read about volcanoes, you've probably heard the terms active, dormant, or extinct. There's a lot of different ways to classify volcanoes. So when people ask me what the different types of volcanoes are, that's actually a much more complicated question than you think, because we categorize them so many different ways. And this is one of the most well-known ways that we do that. And basically, we're going to use the definitions that are used by the United States Geological Survey, which is that active is any volcano that has either erupted in the Holocene, which is the current period of geologic time we're in and covers about the last 10 to 12,000 years, or any volcano that is considered to have the potential to erupt again in the future. Notice the definition of active is not that it is currently erupting. If a volcano is currently erupting, it certainly counts as active, but it's not necessarily a requirement to be called active. Dormant is a volcano that isn't currently erupting, but could erupt sometime in the future. It can still be showing signs of unrest, like hydrothermal activity or earthquakes or things like that, but be considered dormant because it's been so long since it's experienced activity that is abnormal for that system. But again, these definitions change very much depending on who is using the term. That's what makes them kind of confusing. Many geologists use dormant differently than other geologists. It's kind of a personal opinion definition, which is where we kind of get into trouble with the word dormant in particular. Even the term extinct is not necessarily as black and white as it should be. Extinct is supposed to mean that it will never erupt again. And that's usually based on the fact that it hasn't erupted in millions of years, or that we have no evidence of a magma source beneath the volcano. But there have been extinct volcanoes that have erupted. So that is generally how we try to refer to them and how a lot of our volcanic predictions are based off of. But particularly with dormant and extinct, those definitions are a bit more subjective, and different volcanologists and different observatories in different countries may use them a little bit differently. Another way that volcanoes are categorized is by their shape. So a cinder cone, these tend to be very small and erupt a lot of fragments that fall around it to form the cone shape. They also typically have a crater opening at the top. A composite volcano, also called a stratovolcano, those are usually very steep and they have alternating layers of lava, ash, and other volcanic ejecta. They tend to be very large, and a lot of very famous volcanoes are stratovolcanoes, like Mount St. Helens in the US or Mount Fuji in Japan. Lava dome is formed by really, really thick lava. So the lava can't really travel very far from the vent. They kind of just end up looking like a little blob. A good example of that is the Nova Rupta volcano in Alaska. If you ever have seen a picture of that or want to look up a picture of that, it is quite literally a blob. It doesn't look a whole lot like a volcano, to be honest. A shield volcano is built almost entirely of lava flows. They are usually made up of a kind of rock called basalt, which is very fluid and travels much farther distances than if the lava were very, very thick. And that's what allows it to build its characteristic, long sloping shield shape where it gets its name. And the Hawaiian Islands are probably some of the most well-known shield volcanoes. Another way you can categorize them, we're halfway done with categories, is effusive versus explosive volcanism. Generally, volcanoes tend to have either effusive or explosive type volcanism, depending on many factors, including the gas content and the geochemistry. But there are some exceptions to that, which we'll go over. Explosive volcanism is just what it sounds like. It's a volcano that explodes. And this happens because the lava is really, really thick and there's a lot of gas in the lava. So if the lava is really, really thick and hard to move and it's full of a lot of gas, that pressure is going to keep building and building and building until an explosion occurs. Effusive volcanism is when the lava is a lot more runny, so the gases can escape a lot easier and there's not as much pressure. So instead of exploding, they have a comparably much more gentle eruption with beautiful long lava flows. This is the kind of eruptions that happen in Hawaii, and the most recent eruption in Iceland that made the news the past few years, those were also considered effusive volcanism. I do want to note that the main exceptions to these is that there's a type of eruption called a phreatic eruption, which is essentially a steam-induced eruption as opposed to being driven primarily by magma and gases in the magma. What happens is that in the magma reservoir, water gets into the reservoir, flashes to steam, and then it's exposed to all of that heat and pressure inside the volcano, which causes an explosion. Those are typically on the smaller side compared to most explosive eruptions, but they are nearly impossible to predict, unlike traditional eruptions, which we have a number of methods to monitor. This is the kind of eruption that happened in New Zealand at the White Island eruption in 2019 was a phreatic eruption, although that volcano is typically an explosive type volcano anyway. But that type of eruption can also happen in effusive type volcanism. Some of the Hawaiian Island volcanoes, which are the pretty much classic effusive type volcano, will go through cycles where explosive volcanism occurs. And this is because of phreatic volcanism. The last way I'm going to go over is the volcanic explosivity index. So this is a way that is that's primarily going to be used for explosive volcanism, and it's how we rank the severity of the explosions. It's referred to by its acronym, which is the VEI index. It's a scale that goes from 0 to 8, with 0 being non-explosive and the other categories being determined by the volume of material that's exploded out of the volcano. I am also going to take this opportunity to address the term supervolcano because it's going to come up later when we talk about misconceptions quite a bit. Supervolcano is not really a real term in volcanology, and pretty much every volcanologist I've ever met absolutely hates that word. The eruptions at the level of a VEI 8, or occasionally I've heard it applied to VEI 7s, can be referred to as super eruptions. But the reason we don't like the term supervolcano is because that very much implies that every eruption that volcano has is a VEI 8. And that is not going to be the case, maybe not 100% of the time, because I'm not going to say 100%, but I've never heard of one where that's not the case. So in fact, a majority of volcanoes that have a super eruption will only ever have one super eruption, and the rest will be smaller, more typical eruptions. Even at Yellowstone Volcano, which is one of the few that has had more than one super eruption, it's incredibly unlikely to ever have another one. And in fact, Yellowstone has had multiple eruptions since the last super eruption, and they have all been, compared to super eruptions at least, rather unimpressive. So if anyone tells you that the next eruption at Yellowstone is going to destroy the planet, you can tell them that the next eruption at Yellowstone actually already happened thousands of years ago, and the planet is still here, as far as I'm aware, anyway. Why do we care about volcanoes other than it's interesting, right? Eruptions are dangerous. Even smaller eruptions can be dangerous if it happens in a populated area or if it produces a lot of ash that gets carried to surrounding areas. So we're going to talk about the main volcanic hazards that you should be aware of. The one on the left is going to be volcanic ash. It really isn't anything like normal ash. A lot of the times people are picturing like ash from a fireplace, but that's not what it's like. It's tiny rock fragments. So imagine breathing that in. That would be very uncomfortable and could definitely cause some respiratory problems if it's breathed in for an extended period of time. And the weight of the ash very commonly collapses rooftops, especially if it gets wet. If you have a rooftop with a lot of ash on it and then it rains, oftentimes roofs will collapse with people in their homes when they're sheltering from an eruption. So that is something that's very important to be aware of when you're considering volcanic safety. There's obviously lava flow. A lot of people assume that lava is going to be the biggest volcanic hazard you're going to have to worry about, but it's actually one of the easiest to avoid getting injured from because lava moves a lot slower than they make it look in cartoons and movies. Lava isn't like a pure liquid. There's lots of stuff in there, so it's much more similar to the thickness of like corn syrup, and it moves pretty slowly. It can be a big threat to stationary things like houses and buildings or other infrastructure, but to people who can just generally move away from it in most circumstances, the other hazards are going to be much more dangerous. Another hazard is pyroclastic flow, which is essentially a mass made up of ash, rock fragments, and other ejecta moving really fast downhill. It can reach 700 degrees Celsius or 1300 degrees Fahrenheit roughly, and can move downhill at 200 meters per second or 6 feet per second. So it's incredibly dangerous to be caught in one. These two on this page are definitely the more dangerous of most of them, majority of the time. There's lahars, which is on the right. That's like a volcanic mudslide. It has a consistency a bit like concrete, and it moves down valleys sometimes over 200 kilometers an hour, which is about 120 miles. And it essentially buries everything in its path. It very commonly fills in valleys. So if you have a lot of infrastructure, a lot of people living in valleys, and there's not a good warning because it goes so fast, that's another thing that you really want to keep in mind if you're living in a volcanic area or trying to prepare for an eruption. Lahars are actually one of the least well known as well, even though they're responsible for quite a few of the historic deaths related to volcanic eruptions. In the US, our volcanic monitoring agency, the United States Geological Survey, is our main monitoring agency, or their partners. And if you go to usgs.com, they've made hazard maps for a lot of our active volcanoes. So you can see if you live in an area that would be likely to be affected by those kinds of hazards. They also have something called the Volcanic Notification System, which will send out alerts related to changes in volcanic activity at any of our volcanoes, which you can sign up for online. So if you do live in the US, I would highly recommend signing up for these. But if you don't live in the US but live near another volcanic center, maybe look into your local agency and see if they have anything like that that would be available to you. Information really is power when it comes to protecting yourself from these kind of situations. So any information that is made available to the public, it's really important to make sure that you're seeking that out if you live in an area that could be exposed to those kind of hazards. What should you do during an eruption? I get asked this question a lot, and I have made some content before kind of going over it briefly, but the best answer I always have is to follow the recommendations of authorities where you are. Before an eruption happens, it's always a good idea to have a go bag with emergency supplies for a few days, one for everyone in the family. I would also highly recommend knowing what protocols are for emergencies for your jobs, but especially your kids' schools, your pets' daycare, your parents' nursing homes. You want want to know what the protocol is if something happens and what to expect. Are they going to expect you to come pick them up? Are they going to take them to a secondary location where you pick them up? If you don't know that kind of information, an emergency happens, and for whatever reason you can't contact them or they can't contact you, they could be taking your loved one somewhere else for safety and you not know where they are. So you really want to know what those emergency plans are for everyone in your family and make a plan with your family what you would do if something happened. As I said, for USGS volcanoes, the authority that you're going to want to, or US volcanoes, the authority that you're going to want to listen to is USGS and the partners that they work with. But you want to know who that authority is in your area if you live in a volcanic area, and during an emergency, that's who you want to listen to. I do make a lot of content on social media about volcanoes and volcanic eruptions and safety and those kind of things, because I think awareness is really, really important. And it's sometimes hard for people to find that information elsewhere, but there is no better resource than the actual scientific agency in charge of that particular volcano and following their advice, especially during a real emergency. I do not want people pulling up my volcanic hazard videos on TikTok or Instagram during an eruption for advice. I want you going to the people who are actually an authority on that situation when there's an actual emergency. So you should be listening to the scientists and people who've made protecting others from volcanic hazards their life's work, essentially. So that is going to be my main advice, is to go to as many websites with good volcanic preparation information ahead of time. There's some of them for the US, at least on here. Again, I'm not going to be able to give information on every country with volcanic hazards. So you want to find out what is applicable to where you live. But you can do that to prepare for volcanic eruptions. And then during an emergency, you want to be listening to official agency channels. And while they're giving you directions, listen to the directions they give you so that you can get out of the situation safely. Can we predict volcanic eruptions? I cannot tell you that a volcano is going to erupt at a particular time, on a particular day, in a particular way. Volcanic systems are massive. They're driven by processes happening in the entire interior of the earth, pretty much. So there are far too many variables for me to tell you, oh, this volcano will erupt next Tuesday at 7:30. Anyone who tells you that they can do that probably doesn't know what they are talking about. But that does not mean that there are no warnings to eruptions, and that does not mean that we have no way to prepare for eruptions. Most eruptions are going to have pretty significant warning signs leading up to an eruption, and really large eruptions especially are going to have warning signs, which is what modern day eruption prediction and monitoring the volcanoes centers around, is searching for those warning signs so that we can prepare ahead of an eruption. Some of the warning signs that scientists look out for are increases in earthquakes. That's both the strength of the earthquake and how often they happen. It is important to note that a warning sign is an increase in earthquakes, not just the presence of earthquakes. For many volcanic systems, daily earthquakes are normal, and they do not necessarily indicate that the system is changing or gearing up for an eruption. That's the case for Yellowstone. Earthquakes near Yellowstone happen every day, even larger ones, often right near the volcano. They are neither a sign of an eruption in the future, or are they going to induce an eruption. There's no evidence that it will do that, because at Yellowstone, earthquakes are normal background activity. So if those suddenly increased above normal activity or suddenly increased in strength for a consistent period of time, then they might interpret that as a sign that the volcanic system is changing and that there might be an eruption. But in the event that that happened, the Yellowstone Volcano Observatory would put out an alert saying that that was what was happening, so that people could prepare. New areas of steaming or fumarole activity, again, emphasis on new, would be a sign that potentially the volcano would eventually erupt. Lassen volcanic area has had fumaroles, so their presence does not indicate an impending eruption. But if new areas started popping up, then that might be something that the observatories might look into. Changes in heat and thermal activity is something that's really useful in predicting eruptions. Often you can find thermal images where the heat is greater right before an eruption than it has been historically. So that's an important way that they monitor for potential eruptions. Swelling in the ground surface. The ground will often start to swell if there's new magmatic activity, but this is one that can also be very misleading if you're not really familiar with the system that we're talking about. For Yellowstone, for example, people often cite ground swelling as a reason for Yellowstone showing signs of an impending eruption. But again, that is not the case at Yellowstone, because Yellowstone is an incredibly active area hydrothermally with hot water running under the ground. And that's why there's famous geysers at Yellowstone. So movement of water can also cause that swelling in the ground. Yellowstone is often referred to as breathing because the ground regularly moves up and then back down as that water movement affects the landscape. But for anyone who's still skeptical, if you look at the ground elevation at Yellowstone over the last several hundred to thousands of years, the elevation at Yellowstone is actually decreasing overall since the last major eruptions. Even though there are small periods of uplift due to the hydrothermal activity in the area, overall, there's not an increase in land elevation, there's a decrease. So we really can't use that to claim that an impending eruption at Yellowstone is in any way imminent. If I can get the next slide to go, I'll continue. Okay, on that note, we're going to talk about misinformation on volcanoes, which I've kind of been addressing a little bit on one particular volcano so far, but there's a lot of misinformation out there about volcanoes. The biggest culprit is definitely Yellowstone, which is why I keep mentioning it. And yes, I am going to keep mentioning it a little bit more because it's a very good example. But it's not just Yellowstone. There's this kind of information out there on a lot of volcanic systems, and I honestly think it's been getting a bit worse over the last few years. People are more interested in volcanoes now than I think they maybe used to be. We all had a lot of time during quarantine, and the Iceland eruptions got a lot of people interested because they were more accessible than a lot of past eruptions, which is really great. It's really great when people are interested, and it's great that people want to learn, but that also means that people are going to start trying to profit off of this interest that people have in it. People want to get you to click their articles. They want to get you to watch their documentaries, watch their TikToks and YouTube videos, and fear sells. So they have a pretty big incentive not to tell you the whole truth of the situation. And I say that as someone who makes content on volcanoes on a lot of those platforms, but you better believe the videos where I say Yellowstone is not going to destroy the planet gets a lot fewer videos than a lot fewer views than the ones that say that an apocalypse is coming. But the fact is, with volcanoes, while they are very interesting, most of the time we're not talking about a cataclysmic planet-ending situation. How to avoid misinformation. So you want to go to official sources, scientific sources as much as you can. I always hate that I have to recommend this only because a lot of scientific sources are not written in a way that's easy to understand by regular people, which is really, really unfortunate. It's not always communicated very well. For some situations, there is a lot of good information out there. Yellowstone is one of those situations. There's a lot of really good publicly available information that's written specifically for non-specialists. Luckily, science communication is becoming a bigger priority for a lot of places now. So there is a little bit more information out there, but you want to try and get your information from as official a source as you can possibly find. If you're getting your information from a science communicator, you want to make sure that that person actually has experience in the field they're communicating or has worked in that field. If there are publications meant for public consumption put out on the topic, read those as opposed to reading regular newspapers like, Daily Mail or Washington Post, even New York Times or BBC. They're great publications, but they are not scientists, and sometimes, even if accidental, a lot of the times the information ends up being incorrect. So if you can find sources like that, it's really best to try and get one that's directly from a scientific agency. In the case of Yellowstone, as I said, Yellowstone Volcano Observatory puts out more publicly available publications meant for outreach, I think, than maybe any other observatory that I know of. They have multiple pages dedicated to debunking probably most of the rumors that you've heard about Yellowstone. Even if you're one of those people that wants to know, okay, what would happen if you hit Yellowstone with a nuclear bomb? They literally have a page on that, actually, because they get that question so often. So I really highly recommend looking at those websites if you want that kind of information. The scientist in charge at Yellowstone actually put on a publicly available talk in 2021 addressing all of the most common misconceptions about Yellowstone that I really, really encourage you to watch after this presentation, because this talk and other information put out by Yellowstone Volcano Observatory is where pretty much all of my Yellowstone information comes from, because I don't research Yellowstone. I research other volcanoes. So even as a scientist, even as someone who studies other volcanoes, I am still going to look to the ultimate authority who spends all their time researching that for my information. So if you have access to that, which in the case of Yellowstone, you have access to that original source material yourself, I really, really recommend looking at that yourself in addition to watching the creative content that you enjoy watching. Me studying some other volcano doesn't necessarily automatically makes me an expert on every volcano, and you should really be aware of anyone who acts like it does. You want to talk to the people who are the experts. Sometimes that's not always possible, but when it is, just try and make sure your sources are reliable as possible, and news outlets and documentaries are not really going to be reliable sources. If the absolute only source you have access to on a particular topic is news articles, which definitely does happen, you want to watch out for a few things. One thing is the phrase "scientists have said." This is a very volatile phrase, in my opinion, because if they write that scientists have said something and they don't specify what science or what scientific body said that, they probably made it up. Or if they didn't make it up, they got it from someone else who made it up, who also said scientists say, and it's just an endless chain of people with no actual source citing each other. If they do say which agency or scientist they got that from, do not assume that everything in the article is approved by that agency. Even me, I cite USGS stuff a lot, but that doesn't mean that everything I say comes directly from USGS. It's still just my interpretation of the information that they put out. So if you have access to that original source material and it's written in a way that is good to understand, then you want to try and seek that out instead, even though that's not necessarily possible in every situation. But just continuing to use Yellowstone as an example, I actually had to write to a newspaper, an online newspaper, and get an article taken down from UK Science Express, and it says science in the title, but because they stated that Yellowstone Volcano is on the Ring of Fire. And the Ring of Fire is a term used to refer to a chain of volcanism happening around the edges of the Pacific Plate due to interactions between the Pacific Plate and the surrounding plate. There's a map of it here. Not only is Yellowstone over 1,300 kilometers away from the Ring of Fire, it's actually a completely different kind of volcanic system. Yellowstone is a hotspot volcano, and Pacific Ring of Fire volcanoes are most likely going to be subduction zone volcanoes. So they are actually a completely different kind of volcanic system. They first claimed that it was on the Pacific Ring of Fire, and then after that, they claimed that Yellowstone was overdue for an eruption, a phrase which I'm sure many of you have heard, and we're going to talk about that for sure. This is one piece of misinformation that's been debunked many, many times by the Yellowstone Volcano Observatory, but because there's so much information about Yellowstone flooding Google, it's, even if you know it exists, it can be kind of hard to find the direct source on that. But there is no such thing as an overdue volcano. Volcanoes do not work on a schedule like that. Where is the idea that Yellowstone is overdue from? My best guess would be this documentary that says super volcano and literally says overdue on the front of it. That would be my best guess. And similar kinds of articles and publications like that. And it's not anyone's fault that they believe that, because this is supposed to be a science documentary, right? People think that they should be able to rely on that kind of information. Sometimes it's not that the information they're presenting is an outright lie. Sometimes it's just leaving out important things that make you less afraid for your life, because you're more likely to keep watching it if you're afraid of what's happening on the screen. The other way that they got this idea that it's overdue is what they did is they took the intervals between super eruptions at Yellowstone, averaged it out, and said, okay, it's been longer than that average since the last super eruption. It must be overdue. Here's the thing about that. Scientifically, that is not scientifically sound. That's not reliable. But even if we were to use that, even if we actually did the math, Yellowstone wouldn't be overdue for thousands of years. They did the math wrong, or they got the wrong numbers. But if you actually look at the timing of the intervals and do exactly what they claim they did to get the idea that it's overdue, it is not going to be overdue for thousands of years. And even when theoretically we get to that time, it will still not be overdue, because there's no such thing as an overdue volcano. back to the article, which luckily they did take responsibility for and they took down after I emailed them, which it's great that, you know, they took it down. But the reason why I'm mentioning this is that right after stating those two incorrect statements that USGS actually already had pages dedicated to debunking, they then quoted USGS on something completely unrelated to those statements, which makes it seem like the entire article is USGS approved or using USGS information and has merit. This is an incredibly common practice where they directly quote a scientific body to make it seem like all of their information is based off of scientific findings, but then state things that have no scientific basis, or worst case scenario, like what was happening in this article, they directly contradict the agency that they're claiming to cite. And unfortunately, with volcanoes and probably other kinds of science, I'm not sure, but this is an incredibly common practice when it comes to reporting on these kinds of things. Last example probably on Yellowstone is this video on TikTok, which I'm not going to show the whole thing, but there's many videos like this. There's a video on TikTok that went viral last year, got millions of views. It's Yellowstone apocalypse content. They essentially listed all the things that would supposedly happen in the next eruption at Yellowstone. You know, everyone's dying. The world is dying, basically, was what the video was about. And then they claimed to be quoting a very well-known Yellowstone researcher as their primary source for this content. Now, that was obviously not the case. And many people who are in the volcanology research community have read this person's work and know that that's not what they are claiming. The researcher didn't say any of that information would happen in the next eruption. What happened was they had done a lot of really incredible research on what has happened in past large eruptions at Yellowstone. And then the people making that video took that information, assumed it would apply to the next eruption, and made it seem like that scientist endorsed their content, when in fact he, along with a majority of Yellowstone researchers, have made multiple statements that Yellowstone may actually be in a dying cycle, or that the conditions for an eruption do not currently exist at Yellowstone. The examples for Yellowstone misinfo are the most numerous, but these kind of statements, again, happen all the time on volcanic systems. After the eruption in Hawaii last year, I saw a lot of people saying Hawaii was on the Ring of Fire and going to set off the Ring of Fire. Hawaii is also not on the Ring of Fire and also a hotspot volcano. So that is not applicable to that situation either. You've probably heard the phrase something is going to set off the Ring of Fire before, and that is not possible because the Ring of Fire is called the Ring of Fire because eruptions have already consistently been going off on it for millions of years. Just last year, there were over 50 eruptions along the Ring of Fire. And even if that weren't the case, there's actually no evidence that a volcanic eruption at one volcano on the Ring of Fire would induce an eruption at any other volcano along the Ring of Fire, even though I'm sure that's in contradiction to many videos you've seen on the topic. They are all separate systems, even though they are on the edge of the Pacific plate. So unfortunately, as fun as they may be to watch, a majority of videos that you see talking about a volcano destroying the entire planet, or probably even a large portion of the planet, is likely fear-mongering and full of inaccuracies, even if it might be a documentary. Even the idea that super eruptions are the largest, most dangerous kinds of eruption on the planet is actually inaccurate. There is a kind of incredibly rare eruption. It's called a flood basalt eruption. And during these eruptions, massive amounts of lava are erupted. The largest of these is called the Siberian Trap. So you can see how large it is on the map, and it covers an area of about 2.5 million square kilometers. So you can see again how just what a large area was covered in lava. So despite the fact that these are not explosive eruptions and they are very, very rare, they erupt so much material in such a relatively short period of time that these would actually be significantly more dangerous than even a super eruption. There is currently no reliable correlation between super eruptions and mass extinctions, while there is quite a bit of research on the role that flood basalts have played in mass extinctions throughout history. So now that I've told the internet about something more dangerous than a super eruption, I'm sure there will be 3 fear-mongering documentaries about it released by this time next year, most likely. But so that's the essence of it, is you really want to be mindful of what you're consuming and try and do your best to verify any of that with the actual scientific bodies that are doing this research, and a lot of whom are trying to put out more and more publications that are easy to understand. I do want to leave time for questions, so I will end here with my advice for people who want to get into the geoscience field and people who maybe aren't necessarily interested in as a career, but would like to learn more about it. If you would like to get into geoscience as a career, the best advice I can give is to ask people who work in the field what their experience has been like. Even if you've never met them, many of us would be very happy to answer questions. So, find a geologist on LinkedIn or on a university website and email them and see if they're willing to talk to you. I can answer questions about my experience in marine geology and volcanology, but I'm really at the beginning of my career, and I also don't really know what the life of a hydrogeologist or a sedimentary geologist or someone in a different specialty is going to be. And it's kind of hard to find that information online accurately described. So my best advice is honestly to network and ask a lot of questions so that you can find out what each specialty is really like and what opportunities are out there for geoscientists, because there are a lot of opportunities out there, but you want to make sure that the opportunity you're pursuing is right for you. And the best way to do that is to talk to the people who are already doing it. For more about some reliable sources, the Smithsonian Volcanism program has a tracker of current eruptions that you can click on to learn more about volcanic systems. These are all really good non-specialist friendly places to look for accurate information on volcanoes if you want to learn more. For the US volcanoes, there's a lot of great pages on usgs.com, the National Park Service website, and also Oregon State University has a ton of incredible info about volcanoes across the globe, and anyone can access these websites, not just people within the US. So other university sources, if you have a university in your country and you live in a volcanic area, then they might have some publications out that are related to the volcano you're interested in. And as I said, this global Smithsonian website, they actually have a running page of all the currently happening eruptions, and you can click on it and it'll take you to a page about that volcano. So it's a very, very cool resource to have, and you can go there and be confident knowing that, okay, this is reliable information with accurate descriptions of what the hazards would actually be at that volcano. And with that, I will take any questions people have.
Thank you so much, Denali. That was incredible. Thank you again for the wonderful presentation. We have a couple of questions.
Okay.
First question is from Roger. Did you explain why hotspots should remain stationary for millions of years?
So that's one of the things that we actually don't really know. Like I said, hotspots are kind of one of the big remaining mysteries in geology. We don't know exactly how or why they form or why they stay stationary. We know that material in the mantle is subject to convection currents and material moves. So we don't actually have a good explanation for why they stay in one spot. There's a lot of ongoing research about it, but as far as something that's conclusive and that we're sure about, we don't currently have anything like that, which is why it's such an exciting area of research, because that's definitely something we would want to know. That's the exact same kind of questions that researchers are asking right now.
Yeah. Next, Anna. It has two questions. What advice would you give to a prospective volcanologist looking to do masters or PhD in the USA or abroad? How would you recommend recent BS geology graduates who are looking to find jobs in volcanology in the USA search or reach out to find positions?
My advice for both is going to be related to networking. Geology and volcanology in particular is a very, very small world. A lot of the times when you're looking for jobs, people are going to go with people that they've met before or that they have worked with before. And so the best thing you can really do for your career is network. Obviously, it's really, really great to have good grades and good research and participate in all that. But you also need to really be connecting with your fellow scientists so that they might want to work on collaborations with you or bring you on for jobs. That's going to be my same advice both for volcanology and for geoscience, is you really want to be participating in the geoscience community so that people know you and are excited to work with you when they see your name come up in job applications or PhD or master's program applications. Get as much research experience as you can if you want to go into a master's or a PhD, and make sure you're networking with your fellow scientists.
Yeah, there are a few more comments, but these are actually not any questions, but general comments.
Okay.
Elba is saying, hello, thank you for the wonderful presentation. I am glad yet you touched the fact that many people read information on the internet and without checking its source, they share it and think that's truth. Nowadays, we got access to a huge amount of information.
Yeah,
And
that's
that's right.
very, very true. Yeah. It's getting progressively more and more difficult to tell if it's from an accurate source. So
There's another comment from Karen, I guess. No comment, no questions, but want to thank you for incredibly clear and layperson friendly presentation.
thank you. You're welcome.
So if you have any questions, please comment and we can ask Denali if you have any questions. This is the time for Q&A.
Okay, got one that said, are there any other websites that have good volcano information? The ones that I put up in the slide are going to be the most consistent, but really any university affiliated website is going to be a good one to go to, and it's probably going to be a better source or a more reliable source for people outside of the US, because a lot of what I'm familiar with is US based. But many universities make preparing non-specialist friendly content a part of their curriculum, or have university run blogs or things like that. Those are really good sources. And also, like I said, if you can't find a source that's directly related to an agency or scientific body, it is okay to get your information from other sources, but you want to make sure that that source you're talking to has actually worked or studied or is involved like that in some way with that career field and with that research, so that you know that they are interested in getting you the most accurate information. So I know a lot of people nowadays have a very hard time looking for information beyond, TikTok or YouTube. And if that's how you like to get your information, sometimes that can be okay, but you want to make sure that the people you're watching and the people you're interacting with are actually credible about what they're saying and what they're talking about, because sometimes they're not. So my best advice would be university websites, and then just to verify that the other people you're interacting with and getting your information from are actually part of that research field.
We have a few more minutes. Everyone, if you have any questions, please comment down.
Yes, so I didn't talk about the relationship between volcanoes and mineralization. For mineralization, a lot of the times volcanoes can be a very important source of minerals, and later on, sometimes that is where we grow agriculture, where there's been minerals and deposits made in the soil that are friendly for agriculture, or sometimes they'll later be mined. I didn't focus on it so much in this talk, mostly because I wanted to gear it more towards a very broad overview of volcanoes and volcanic systems, and that's also not the area that I research, so I don't know that I would be able to speak with very strong authority on that topic if people were to ask a lot of follow-up questions.
I think we don't have any further questions. Oh, just got a question.
Does underwater pressure levels at great depths have an effect on submarine volcanic eruptions? Yes, that's actually a very interesting fact. So volcanic eruptions that are very, very deep beneath the water do not erupt with necessarily the same level of explosivity as surface eruptions. And that's primarily because of the content of the rock. And that's also, like you mentioned, because of the pressure. There's a kind of volcanic rock called pumice. And sometimes when it erupts at submarine volcanism locations, it will float to the surface because it has air bubbles. But depending on the depth, if it erupts at a very, very deep level with a lot of pressure, the pressure will prevent the pumice from floating to the surface, and it will make it more dense so that it sinks. So the pressure does affect the severity of the eruption. I know maybe sometime last year there was a video that went viral about Mariana Trench volcano potentially erupting and also destroying the planet. That also would not be possible because while there are volcanic eruptions at the Mariana Trench or in that general area, because it's submarine volcanism and that's an area that's subject to it, the pressure down there is going to be so intense that even if it is a large eruption, it's not necessarily going to have a huge effect on the surface, other than that it's going to be really, really interesting. Or if you're a boat right above where it's erupting, that would be a very bad day for you. But as far as for the planet as a whole, it wouldn't really be as much of an issue because that pressure is going to control the eruption in some ways. So someone asked a question about the interest in volcanoes for the economy and economics, and the primary relationship between volcanoes and the economy is going to be with agriculture. Pretty much every very strong, fertile area that we grow a majority of our food on is all related to volcanic soil. And for another thing, most rock on the surface was at some point, even if it was metamorphic or sedimentary, at some point it was a igneous rock that was broken down and became those other forms of rock. So if we want land to walk around on, we're going to have volcanism because that's what produces the land that we walk on. And if we want to have food, then we also have to have volcanism because volcanism is what delivers all that important nutrients to the land that we can then grow our food on. It's one of the reasons why so many volcanic islands are areas with very strong agricultural holds, because the nutrients is so rich that even though it's a volcanic area, it's worth it to be in those areas so that we can grow the food that we eat. And then I got another question about the positives of volcanoes for our planet. So it would be pretty much the same as the economic interests, in that volcanoes do contribute very much to the nutrients in our soil. They also produce the land that we live on. And they also are actually very important for a number of species. For above ground volcanoes, there are another of animals, or in particular birds, that lay their eggs near volcanic areas because the warmth from the volcanoes underground serves as a way to incubate their eggs. And especially at mid-ocean ridges, without mid-ocean ridge volcanism, the ocean would be completely different. A majority of the iron that is used by photosynthesizing creatures in the ocean is provided by mid-ocean ridge volcanoes. There are entire colonies of submarine organisms that live at hydrothermal vents and other areas associated with volcanic activity. So without submarine volcanism in particular, it really would change a lot of fundamental things about the cycle of life in our oceans, which is another thing that we use for food and to fuel our economy and things like that. There's no telling what our economy or what the ocean would look like if we didn't have submarine volcanism, because like on the map I showed earlier, there's a lot of them. A majority of our volcanism is from that, and it has huge impacts on our oceans, which impacts all of society overall. So. All right. You're welcome. Any other questions?
I think we can take one more question, and that's from Seth. He said, "I would love to ask you about the new rifting in Africa. Do you have some information about the evolution of this new rifting, also the impact of also the impact of the latter on the progress of African plate to the European plate.
Yes, so you're referring to the East African Rift, and it's actually been ongoing for a few millions of years now, but it every few years it makes the rounds in the news. But it is a very, very exciting. Essentially, the East African Rift would eventually become similar to what the mid-ocean ridges are, like the Mid-Atlantic Ridge. So it's a divergent boundary where two tectonic plates are moving apart. And as they move apart, there's an opening being created in the center. It's called rifting. And in the next several millions of years, long after we're not here, but in millions of years, it would be a new ocean basin, much like the Mid-Atlantic Ridge created the Atlantic Ocean Basin. The East African Rift is in the process of creating another ocean basin in that area, which is very, very exciting.
All right. Thank you, Denali, again for the wonderful presentation. And thank you everyone for joining us today. Do not forget us to join in the upcoming days for our series of these live sessions. Thank you again, everyone, and we wish you a great rest of your day. Thank you.